My name is Paulo, and you probably have heard that. Today we're going to talk about scratching the surface of homomorphic encryption and just a few heads up, okay? So the first one is this is not a very technical conversation or presentation, although I will talk about technical stuff, okay? Um, but if there, for some reason, everything froze on my screen. Oh, okay, it's back. All right. So if I will talk about complicated subjects, but to be honest, I will try to exemplify along the way, so we can keep the knowledge level at the same level for everyone. So without further ado, let's jump into that. So this is the agenda for today. We're gonna talk about cryptography, types of cryptography algorithms, ciphers, how we do more modern cryptography, and only then we'll talk about homomorphic encryption. So I'll also tell you what's out there, what to look out for, and show you some examples. So bear with me. Without further ado, what is cryptography or cryptology? So, and apparently they are synonyms. I realized that recently. So that's a field of study about the techniques used to create secure communications. All right, so that's very interesting, but also very old. So the word comes from the combination of two ancient Greek words that can be loosely translated to write secretly. Of course, I mean, the words mean different things. I'm just being a little bit creative here. But the important thing to understand is that this is something that has been on people's mind for a long time. So one of the oldest cryptography based mechanisms that we know of is called the citale. You probably saw that in some series or movies that depicts the Roman Empire or something similar to that. But basically, it works the following way: a person would have either a paper or a piece of cloth or something made of leather, back in the day, and it would wrap around a specific rod, which would have a unique diameter, okay? And then you write it down, what's the message he or she wants to convey to the other person. If you just unwrap that, it's very hard to understand exactly which words are actually written in that. So the other person on the other end of the communication line must have an exact replica of that rod, same diameter, same angles and everything. So it's a type of low-tech encryption, but honestly, it worked really well for a long time. But in the modern days, and not so modern really, you've probably seen or heard about this one. So the reason why I brought this one up is because most of you probably saw the Imitation Game movie, which talks about the Second World War. And in that movie, they talk about the Enigma machine being used by the army to send messages between different troops that are sitting in different geographic locations. So I want to talk a little bit about that. So the key here is actually those gears, dented gears that you have in here. And they notice that they have like different numbers around them. One thing you need to know is that these gears move independently, and depending on the position of certain gears, whether that wraps around one, all the numbers that you have in one gear, then the second one would move. And essentially, what I'm trying to say is that this is the masterpiece of encryption in that particular tool. Most people actually believe is the power cords at the bottom, where you could wire different characters into other ones. So one example, the letter Q here is actually wired all the way down, to the letter C. So whenever you type whenever you type Q, it actually means C, and vice versa. But the important thing here to remember is the second part, which is the pull cord, is not that hard to break. The one at the top, it is. It's really hard. It's not impossible for today's standards. Like, we have very powerful computers, but it's still quite an interesting machine. The way it would work is you would get the encrypted message and arrange, the combination of those gears, so you see the numbers at the top, to be exactly the same as the one that was used to encrypt the message. So you would also arrange all the power plugs or the pull cords at the bottom. And then once you press one of the buttons, then the letter of the plain text message would light up. So you write it down. So technically you would require 2 people to operate this machine, otherwise it would take a long time. But still, we're talking about 1945. So imagine how complicated this thing actually got over time. And that takes us to cipher or ciphers. There is a lot of confusion about that because a lot of people believe that cryptography and cipher is exactly the same thing. It's not, and I'm here to clear up this confusion. So cryptography is the field and cipher is the method used to achieve that, okay? But cipher refers to an algorithm, usually a mathematical one, capable of encrypting a plain text into the ciphertext. So ciphertext is just another name for encrypted message. So there is a little bit of difference between encryption and ciphers, but for the purposes of this presentation, we will assume they are the same because I don't want to get into the nitty-gritty of those things. Okay. And one thing, remember the side tail that I just showed you, that's actually very similar to the most basic cipher that humans can possibly conceive. So imagine you have 2 alphabets written in 2 pieces of paper, and they are cut in a circle shape, so they would align. Okay, if I agree with the other person that we have to align the letter A, which is part of the blue alphabet, which is the plain text alphabet, to the letter O, which is the encrypted alphabet, the word apple will be ciphered into ODDZS, and you can probably just do a visual connection to the drawing, and you would see that it's actually right. But you also would notice that it's not that hard to break this. So if I observe your encrypted text for a long time, I will eventually recognize patterns, and as soon as I find 1 or 2 vowels, then this becomes like playing the hangman. You're just trying to figure out which letters aren't missing. So it is good, but it's not exactly as complicated than it should be. But how do we do it today? So modern cryptography, because this is a field, humans tend to overcomplicate things, and you know that better than anyone else. But the 2 biggest blocks of or subdivisions of cryptography is we have the symmetric cryptography, where the same secret is used to encrypt and decrypt the data. And the 2 examples I brought before, they are real life examples of symmetric encryption or symmetric cryptography. If the other person doesn't have a rod with the exact same diameter, then the side tail would not work. If the other person receiving the message encrypted by Enigma machine doesn't configure the machine to use the exact same settings, it doesn't work as well. So there is one thing that must be kept between 2 people that must be kept as a secret. It's hard, but it does work. But in computer science, we actually created something a bit more interesting, which is called asymmetric cryptography, which is where you have 1 key to encrypt the data, which is meant to be public, and you can share that around, and we actually have services specifically for that purpose. So if you have ever come across keybase.io, that's precisely their value proposition. And 1 key to decrypt the data, and that one is meant to be really, really private. But we don't have a real life example because it's hard to do that mechanically. It needs to be just mathematically, which is very interesting. But in order to illustrate the process, imagine that Bob wants to send a message to Alice, but privately. No one can actually eavesdrop on the message. So Alice would share with Bob her public key, and Bob would write the message and encrypt with Alice's public key, before sending the message to Alice. Only then Alice would actually be able to use her private key and decrypt that. So this is used in email communication less often than it should, unfortunately, but this is very common, specifically for government agencies or highly regulated industries like the oil industry and so on, because you really don't want, emails leaked to the public for good reason. And that takes us to the homomorphic encryption, because now we are done with 101 crash course of cryptography. We are ready for homomorphic encryption. So what is it? So it's a form of encryption that enables software to perform computations on encrypted data without first decrypting it. And it sounds like wizardry in the beginning, and after you work with that, it still sounds like wizardry. So that's the feeling that you will have even after this presentation. So imagine that you have a server, and that server needs to process a message that comes from the client. So you receive the data, but the data is in the encrypted state. So what you as a server must do is to decrypt it first, so you can look at the data and perform operations on top of that. So let's suppose you are trying to calculate the BMI of an individual. You have to know what's the individual's height and the individual's weight. Otherwise, you cannot actually calculate that. So you depend on the fact that you are able to decrypt that. But because you don't trust that the message will be delivered to the user without anyone else's eavesdropping on it, then you encrypt it back before sending it back to the user. So this is what we do every single day. This conversation that we're having right now is doing exactly that. So we go from that model to this model, which is we receive the data on encrypted state. We don't lose time nor resources decrypting it. We process the data, and because we haven't decrypted that, then that means we don't have to encrypt it back. And then we simply send it back to the user. And it's too good to be true, but before we jump into how that actually happens, I need to just suggest that we pause just for a second to understand what type of opportunity that's bringing into the mix. So here's the thing. Encryption is given different names depending on where it's used. So the first thing you have to do when you're trying to consider I need to encrypt something is to decide first, what are you concerned about? So are you concerned that someone can eavesdrop on your packet while you're sending messages from your machine all the way to the cloud? Because there are many companies that are part of that process, many connectivity providers, and it doesn't go straight to your cloud provider. We all know that, right? So in that case, that's called in-transit encryption, because you're afraid of someone, eavesdropping on the message. So you encrypt that before you send that over the line. But if you are concerned that someone can have physical access to your machine and unplug your hard disk, plug that in somebody else's computer and see the files that you've been working on, then that's called at-rest encryption. So that usually happens transparently. Like I'm assuming that at Xero, being as big as you guys are, you probably have so many security compliance certifications to abide by that the file vault must be enabled by default for everyone or most of you. So that's very common, and most people don't even know that's enabled. But that's a good thing, right? But in the case of homomorphic encryption, that's a new type. It's called in-process encryption, because the data remains encrypted throughout the whole process. So whether that's stored locally or that's sent over the line, you really don't care. The data is encrypted. So that's one step beyond what we currently do, and that's why we should do that in the first place. You increase the threshold for difficulty so other people cannot get access into sensitive data. So this is good, right? So even though you probably got these already, I just wanted to show you like an example with actual numbers and cipher, so people would understand a little bit better of what's going on. So imagine that we have one homomorphic function that performs addition. Okay, so on the left-hand side, you would have the user. The user wants to add 7 plus 5. Okay, so the user would encrypt individually each one of those numbers, would generate this cipher, okay, and send to the add function, which is sitting somewhere else on somebody else's computer. Okay, that function doesn't know that this number is 7, and it also doesn't know that this number is 5, but it knows how to perform addition on top of ciphertext. So the output of that function is yet a different cipher that only the user, after decrypting it, will realize that this is actually the number 12. So if you guessed that the biggest complexity here is on the add function, you're right. And if you guessed that this should probably be slower than just adding 7 plus 5, you also guessed right, because you have way more bytes to process. So that's also given, okay? But how do they know? How do homomorphic functions know that they can actually perform certain operations? So remember we talked about cipher in the beginning of this presentation. We did that for a reason. It's because now you understand exactly what I'm talking about. So different ciphers will be conceived specifically or purposely to allow certain cipher-based operations. So we have accidental homomorphic encryption algorithms like RSA. So we use RSA every single day because it's good, but it's accidentally homomorphic. So if you get 7 and 5 and multiply that in plain text, you get exactly the same answer that you would get with, sorry, probably I need to rephrase that. If you get 7 and 5, multiply that in plain text, and then encrypt that, you would get the exact same answer you get if you get 7 and 5 encrypted before the addition, and you see the results. You can compare them. So, but that's accidentally, okay? The one thing you need to understand is different ciphers will allow you to have different cipher operations performed on top. So one interesting case is the Benelux. So if I want to perform a addition operation on plain text, I would use plus, of course. But if I want to perform that on the ciphered Benelux piece of cipher, then I would use multiply. Sounds a bit weird in the beginning. It's like, wow, I'm trying to add. Why am I multiplying? Don't forget that you're multiplying a cipher. And from a mathematical point of view, it actually makes sense. Don't get too attached to it. The only takeaway from that table here is, actually there are two. The first one is there are way more than this. These are just the tip of the iceberg. But the second thing is you have to know exactly which operations you're going to do beforehand in order to be able to select the most appropriate cipher for your system. So knowing that beforehand is vital, okay? When it comes to when homomorphic encryption was invented, it's not a new concept, but it recently went through some groundbreaking discoveries that reactivated the interest, in that particular approach. So the idea goes back to 1978, which is a long time ago, and as any other field of study, it branched out for different scenarios. So some homomorphic encryption studies were fully focused on making it work on specific hardwares or different ways you would lay out your integrated circuit. And in other cases, it would be somewhat tweaked so you could have either more precision. So you don't work with double values, you would just work with integers and things like that. So instead of doing floating point calculations, you would have to do a integer approximation. So there are all very specific niches, but the one thing I need you to know about is this last two here, the TFHE and the CKKS. We're not going to dive deep into them, but I highly suggest you to take a look at that, because you'd be amazed, what those guys can actually do right now. But before I show you homomorphic encryption, I need to tell you about the use cases. you can use it for. So as I mentioned before, there are highly regulated industries, and the thought of actually moving to the cloud or actually letting someone perform operations on their data is unthinkable, right? But because people don't have access to the original data, they just have access to the encrypted, the encrypted message, then it becomes less of an issue. It doesn't mean that's completely safe. I'm saying that it becomes less of an issue because the third party accessing that data learns absolutely nothing about the client data. And if the third party server gets hacked, that doesn't mean anything. They can't really, encrypt that. And I disagree with what's written on that slide. I actually copied that from a well-known presentation, but I let it here. I left it here just for that particular type of discussion. It doesn't mean that the server location is irrelevant. Data sovereignty is important for a lot of different reasons. That just means that using homomorphic encryption will make the server location less relevant, because now you have a smaller set of concerns about data sovereignty. But that's definitely a step, forward in the right direction, I would say. So I know I talked up homomorphic encryption, and by now you think that I'm just, an evangelist that wants everyone to use it, but I need to talk about the drawbacks, okay? So, as you probably guessed, that's really slow, okay? And when I say really slow, I'm talking about 10 to the power 3 and 10 to the power 6. So it can be 1,000 times lower or 1 million times lower than performing the same operation on unencrypted data. So, there are certain features on your CPU that is highly required if you want to make it doable, or make it run fast enough so you wouldn't pull your hair, basically. But the good news is there has been some improvement, and a really good improvement if you ask me. So since 2009, there has been a 10 to the power 9 improvement. I don't think it will ever get to 1-to-1. It will never be like that, for obvious reasons. But I believe that it is possible that we get to 10 to the power of 2, which is 100 times lower. Okay. And as computers are getting, more and more powerful, then most likely this will become a bit more negligible. And the people who are very into homomorphic encryption are talking about this dream, which is called the HTTP-Z. And first rant of the day. Apparently Z doesn't stand for anything. It's just to add to the confusion that we have with the technology with the overloaded technology terminology. It's really, I wish Z meant something. It doesn't. But the idea would be that you as a user would have one key for every single website. The website would never know which information is yours, because you have to send it to get the response back. And instead of actually a browser which works almost like in a passive way, your browser will be able to actually store information that would belong to that particular web server, but locally. And if you need a backup, the server would send you a backup of your encrypted data, so you can just log it back. So it's a glamorized version of we want cache to work, and we don't want the website, whether that's A, B, or C, to be able to store your unencrypted data. Again, for the reasons that I mentioned a million times during this presentation. But what's out there? This is a very small list. Actually, the list is much, much bigger than that. But there are a few here that I want to emphasize, okay? So we have the Heleap, which is from IBM, and they are relatively old, like 10 years ago, 12 years ago. They were launched, 10, 12 years ago, but they are really, really interesting because they are very well documented. It's a very good space or place to start. The TFHE was actually created by people at Google, and I'm actually interested why they don't write Google here. But Google has been investing really heavily on that because they want the public sector chunk of the market, and of course that's one way of getting it. But I want to show you one of them. So the IBM one that I mentioned is probably the easiest one to understand. So in this case, I would have one vector, and I want to perform an element-wise addition between two vectors. So 1 would be added to 4, 2 would be added to 5, 3 to 6. You can make the calculation there. But just to show you how that would work, how that would not only work, but how that would change the way you make you make your logic, or how you write your code, would be you have to encrypt that, and then you instead of actually using the operator plus, even though you can if you want to in Python to override some of the operators, that's not a good idea. But in this case, they created a method, and that method will actually do all the heavy work for you. If you are interested into the technical details, by all means, jump into it. And if you really like that, please contribute to it, because I think it's a very interesting idea. But I believe that the point that I want to emphasize more is it's not only something doable nowadays, but most of the complexities are being abstracted away from you. So it's just really a matter of including that into your architecture and using it as a unique selling point, whether your customer actually needs that or not. So it's just one more tool in your toolbox. Another thing which is actually, I've been working on that lately, and because NEWA is half funded by the government and it's half funded by the private sector, so we tend to deal with highly sensitive data. So the idea of actually moving data between different industries and put them together so we can create an artificial intelligence model is not really well accepted. People get upset when you say that. So one thing that is being used is we used OpenMind, which is just an extension on top of popular deep learning frameworks, and that one allows you to do two things. The first one is to, instead of actually bring the data to you send the model to train on the somebody else's machine, which is the machine that has the data per se, which is really good. But the most interesting part is that it created the abstraction layer on top of those frameworks, so you can train your artificial intelligence model without knowing exactly what the data is, because again, you still have the patterns, and training is all about recognizing patterns. So that's a way that people have been a bit more acceptant of the idea, and they think it's probably gonna enable some of the machine learning training that we haven't had in the past, because we have all the red tape and the bureaucracy that we have to deal with every single day. Well, there wasn't much, but this is it for me. Do you guys have any questions?
Thanks, Paulo. I'm going to stop the recording so we can get some questions.